Hey everyone, welcome back. We're moving into the next chapter, which is a momentous one because it's chapter 10, so that's a nice number. And it's also marks finishing more than half of the book, which is nice. You guys, once again, have been seeing this every 24 hours, but I've been like zerging it more or less. Um, for you kids out there who doesn't know what that means, it's a term from an old video game called StarCraft, wherein there was like a race that's like a tiny aliens, and each alien did like small damage, but they had like so many of them, and so to swarm, uh, to just create a swarm that just runs through everything full speed and get it going like as fast as possible. That's called zerging it, I guess. I don't know. Maybe I just made that up. I don't know. Um, anyways, so dictionaries. This chapter presents a built-in type called a dictionary. It is one of Python's best features and the building block of many efficient and elegant algorithms. We'll use dictionaries to compute the number of unique words in a book and the number of times each one appears, and in the exercises, we'll use dictionaries to solve word puzzles. A dictionary is mapping. True. Dictionary is like a list, but more general. In a list, the indices have to be integers. In a dictionary, they can be almost any type. For example, suppose we make a list of number words like this: LST equals 0, 1, 2. We use an integer as an... Oh, I need to run that first. We can use an integer as an index to get the corresponding word. Simple stuff. We already saw that in the last episode. But suppose we want to go in the other direction and look up a word to get the corresponding integer. We can't do that with a list, but we can with a dictionary. We'll start by creating an empty dictionary and assigning it to numbers. So this is an empty dictionary. The curly braces represents an empty dictionary. To add items to the dictionary, we'll use square brackets. Number 0 equals 0. This assignment adds to the dictionary an item, which represents the association of a key and a value. In this example, the key is the string 0 and the value is the integer 0. If we display the dictionary, we see that it contains one item, which contains a key and a value separated by a colon. 0, 0. We can add more items like this, as you can see. So essentially, with dictionaries, when you use the brackets, you're essentially saying list. You're saying this in this dictionary. Look for this key. Right. This is the key, and get me what is there at this key. Right. Similar to indexing, but indexing was literally the position, whereas key can be anything. Right. As you can see, it's just some random strings here. Numbers 2 is 2. To look up a key and get the corresponding value, we use the bracket operator. If the key isn't in the dictionary, we get a key error. Len function works on dictionary, returns the number of items. I think it just returns the number of keys. Oh, items, yes. Because items in a dictionary, an item is like a key value pair, like one whole thing. In mathematical language, dictionary represents a mapping from keys to values. So you can also say that each key maps to a value. In this example, each number word maps to the corresponding integer. The following figure shows the state diagram for the numbers. Boom. A dictionary is represented by a box with the word dict. Okay, I don't care about the diagram itself. Creating dictionaries. So you can just create it in one shot instead of creating an empty dictionary and then one after the other, just by this notation, which is essentially curly braces, then your key value pair separated by commas, and each key value pair itself will be key colon value. And each item consists of key. The items are separated by commas and closing. And another way to create a dictionary is to use the dict function. We can make an empty dictionary like this. Yep. And we can make a copy of a dictionary like this. Yep. So dictionary, this is kind of preempting probably what they're going to get into in a moment. Essentially, the dictionary, the same thing that applied to list and it being mutable and therefore funky with how references work, same applies to dictionaries. The in operator. The in operator works on dictionaries too. It tells you whether something appears as a key in the dictionary. One in numbers, true. The in operator does not check whether something appears as a value. So one in numbers will lead to false. even though that is a value. When you do the in operator with dictionaries, it only gives you the keys. It used to be more complex than that, but yeah, that's true. And if you want to check whether it's in the values, you have to use numbers.values. The items in a Python dictionary are stored in a hash table, which is a way of organizing data that has a remarkable property. The in operator takes about the same amount of time no matter how many items are in the dictionary. That makes it possible to write some remarkably efficient algorithms. Yeah, so that's true. So a hash table, I don't know if they'll really get into it, but I'm just going to try to explain this. So essentially, what a hash function does, and which is why the lookup, as he said, regardless of the size, is basically always the same amount of time, because essentially when you first add a key value pair, that key is hashed, aka it runs through some function, um, and then that hash of that key is what is actually associated with the value, right? So that every other time you want to access something at a particular key, you just give it the key, it'll get hashed, and then you'll just retrieve the index right away, rather than having to search through something like a list, which you have to actually check every element, um, or check series of elements. The items in a Python dictionary are stored in a hash table. Okay, yeah. To demonstrate, we'll compare two algorithms for finding pairs of words, where one is the reverse of another, like stressed and desserts. Whoa. Whoa. I did not know that the reverse of stressed is desserts. I'm going to use that with my wife. She's going to love it. Word list equals openwords.text.read.split. So this is essentially a chain of methods. So open words opens a file. The file object has the read method, so you read. Read reads to a string, so you split. So you just kind of chained a couple of different methods, which is totally doable in Python. And then he just takes the length of that, and then reverses, creates a function for reversing the word. So he runs reversed and then joins it. Following function loops through the words in the list. For each one, it reverses the letters and then checks whether the reversed word is in the words list. So this is essentially like we create a word list. We have a reversed word function, which, I mean, we don't even need to get into what it does because we went through this a couple of chapters ago. But essentially, this just reverses the word, and then it goes through each word in the word list, reverses it, and checks if that word exists in the word list, and then increments the count to see how many words, if reversed, exist. This function takes more than a minute to run. The problem is that the in operator takes a minute. It's not taking a minute, but I guess it would on your own machine. I don't know. Which happens most of the time and has to search all the way to the end. There you go. To measure how long I need to pause this recording. Sorry about that. I heard, it's pretty early in the morning and I heard a noise and it freaked me out a little bit because I thought someone fell from their bed. So I went to check. Yeah, that's the kind of anxieties you have when you live in a household with people who have chronic illnesses, but that is what it is. Function takes more than a minute to run. The problem is that the in operator checks the words in the list one at a time, starting at the beginning. If it doesn't find what it's looking for, which happens most of the time, it has to search all the way to the end. To measure how long a function takes, we can use %time, which is one of Jupyter's. Okay, yeah. Len word list exponentiated. The in operator is inside the loop, so it runs once for each word. Since there are more than 100,000 words in the list, and for each one we check more than 100,000 words, the total number of comparisons is the number of words squared, roughly, which is almost 13 billion. True. We can make this function much faster with the dictionary. The following loop creates a dictionary that contains the words as keys. Boom. And now here's a version of the previous function that replaces word list with word dict for word and word dict. If reversed word in word dict, count plus equals 1. Boom. It's as simple as that. It's pretty count plus equals 1. There you go. It's pretty straightforward. Um, so here essentially you create a key, and then the value is actually the count, and then you iterate through each key, reverse it, and then check if it's already exists in the dict, which is the same lookup speed versus like a list, which has to actually go through the list elements and find it. You find it instantly. And just you update that count, and it's as simple as that. Function takes less than 1/100th of okay. Time much faster, whatever. I don't really care about the time. A collection of counters. Suppose you're given a string and you want to count how many times each letter appears. So dictionary is a good tool for this job. We'll start with an empty dictionary. As we loop through the letters in the string, suppose we see the letter A for the first time, we can add it to the, I did not mean to do that. Add it to the dictionary like this. Counter A equals 1. The value 1 indicates that we have seen the letter once. Later, if we see the same letter again, we can increment the counter like this, which is just using the plus equals increment operator, which we saw several chapters ago. And now the value associated with the A is 2 because we've seen the letter twice. And if you just search the dictionary, you'll see that it's updated in place. The following function uses the features to count the number of times each letter appears in a string. For letter in a string, if letter not in counter, counter letter equals 1, else counter letter plus equals 1. And return counter. So yeah, it just basically creates, this is just a basic function for that just takes a string, checks the string, checks the letters in each string, and if the letter is not already one of the keys in counter, it creates it and sets its value to 1, or it increments that value. Each time through the loop, if letter is not in the dictionary, we create okay, yeah. Here's an example. Counter equals value counts Brontosaurus, and then all of the others get added up, as you see. The items in counter show that letter B appears once or appears twice, and so on. Looping in dictionaries. If you use a dictionary in a for statement, it reverses the keys to the dictionary. To demonstrate, let's make a dictionary that counts the letter banana. Banana. I want to start singing the Chicken Banana song, which is really popular with my niece and nephew. Chicken banana, chicken banana. Anyways. For key and counter, print key, BAN. To print the values, we can use the values method. For value and counter.values, print value, 132. To print the keys and values, we can loop through the keys and look up the corresponding values. Print key value. I think there's also a get items method for dictionaries that you can use. In the next chapter, we'll see a more concise way to do the same thing. Yeah, I think there is definitely a dict operation that we can use, or a method. You can put a list in a dictionary as a value. For example, here's a dictionary that maps from the number 4 to a list of 4 letters. Yep, that's true. But you can't put a list in a dictionary as a key. Here's what happens if we try unhashable type list. I believe everything has to be hashable type, which I think could be anything that's immutable, but I'm not 100% sure. I feel like tuples are immutable, so I think they would go in the hash. We'll see. The dictionaries use hash tables, and that means the keys have to be hashable. A hash is a function that takes a value of any kind and returns an integer. Dictionaries use these integers called hash values to store and look up keys. The system only works if a key is immutable. Yeah, so I think a tuple would work. So its hash value is always the same. But if a key is mutable, its hash value could change, and the dictionary would not work. That's why keys have to be hashable, and why mutable types like lists aren't. Since dictionaries are mutable, they can't be used as keys either, but they can be used as values. Yeah, so this last point is relevant because it's here's the thing. There is no, or at least there usually is no secret gotchas in programming, right? If something can do anything, it can do anything, right? And by that, what it means is like, usually when we say like, oh, you can't do this in programming, that's very explicitly like you cannot do that literally, right? not styling or anything like that, which is very debatable, and and how to design an algorithm, even that's debatable. But like in terms of pure syntax, something is not possible, then it's not possible. But conversely, it also means 9 times out of 10 that everything else that is stated everything else that is not stated as not possible is possible, right? So just stating, so that kind of is reiterated here, where you can use dict as a value for dicts. I do want to check if can I use a tuple. I'm gonna check this out. Oh my god, it totally does work. Yes, I was right. Yeah, so tuples are kind of like lists, except they're immutable objects. So once you create a list, you can't, once you create a tuple, you can't like change it. You can just create a new tuple that is maybe a copy of the previous one or whatever. So yeah. And because of what they said here, that means that keys have to be hashable. They have to be hashable. And to be hashable, they need to be immutable. And guess what? Tuple is an immutable type. So there you go. That's something that I didn't even know, that I just kind of put together from what they said, right? And that's kind of the beauty of this. Of programming in general is like that discovery, that sense of discovery, right? And honestly, that's true in all of science. I think the thing that's nice about computer science is it really speeds that process up, right? In terms of that experimentation, it allows you kind of to do that like super quickly, for the most part, while you're building, right? And it's not always true. Anyways. System only works if a key is immutable, so its hash value is always the same. But if a key is mutable, its hash value could change, and the dictionary would not work. Accumulating a list. For many programming tasks, it's useful to loop through one list or dictionary while building another. As an example, we'll loop through the words in WordDict and make a list of palindromes, that is, words that are spelled the same backward and forward, like noon and rotator. In the previous chapter, one of the exercises I asked that checks whether a word is a palindrome. Here's a solution that uses a reversed word. If we loop through the words in WordDict, we can count the number of palindromes like this. We already did that. But now this pattern is familiar. Before the loop, count is initialized to 0. Inside the loop, if word is a palindrome, we increment count. When the loop ends, count contains the total number of palindromes. We can use a similar pattern to make a list of palindromes. If is palindrome word, palindromes.append word. Okay, so essentially it's just doing the same as this, except instead of incrementing the count, just lists all the palindromes, or creates a list of all the palindromes. I think this is leading up into list and dict comprehensions, which it may or may not be. Oh, memos. I don't know what the hell is this about. Okay. Before loop, palindromes initialize an empty list. Inside the loop, if a word is a palindrome, blah, blah, blah. In this loop, palindromes is used as an accumulator, which is a variable that collects or accumulates data during a computation. Now, suppose we want to select only palindromes with 7 or more letters. We can loop through palindromes and make a new list that contains only long palindromes. So long palindromes, forward and palindromes, if blah, append the word. Looping through a list like this, selecting some elements and omitting others, is called filtering. And I believe there's a filter function for lists, methods. Let's see. Dot filter. Okay, never mind. I remember there being a filter method for lists, but I could be wrong. It's called filtering. Okay, memos. If you ran the Fibonacci function from chapter 6, maybe you noticed that the bigger argument you provide, the longer the function takes to run, because obviously it does. It's a recursive function. Furthermore, the runtime increases quickly. To understand why, consider the following figure, which shows the call graph for Fibonacci with n equals 4, right? Because each call to Fibonacci makes actually 2 different calls, arrow pops, and it's actually multiplicative. It's a long story. So here's the stack diagram. Yeah, there you go, the diagram. This, see, like what they're trying to show is like n2 over here is evaluated separately, even though it's also done over here. So just one of the reasons why recursion is not necessarily the best. It's useful for certain very specific tasks, but otherwise where there is no other option. But 9 times out of 10, if you can find a way to do it without recursion, that's probably the better way to do it. Call graph shows a set of function frames with lines connecting. Okay, this is just showcasing. This is just a description of this diagram and why the Fibonacci recursion algorithm gets exponentially worse the bigger you call. One solution is to keep track of the values that have already been computed by storing them in a dictionary. A previously computed value that is stored for later is called a memo. Here's a memoized version of Fibonacci. Yeah, so basically, okay, so that's what an actual memo is. Memoized. I did not know this term, so I guess the more you learn. So known is a dictionary that keeps track of the Fibonacci numbers we already know. It starts with 2 items, 0 maps to 0 and 1 maps to 1. Whether Fibonacci memo is called, whenever Fibonacci memo is called, it checks known. If the result is already there, it can return it immediately. Otherwise, it has to compute the new value, add it to the dictionary, and return it. Comparing the two functions, Fibonacci 40 takes about 30 seconds to run. Fibonacci memo takes about 30 microseconds. So it's a million times faster. Yeah, okay, yeah, that's true. Basically, if you do have to use recursion, you have to use some things like this. Debugging. As you work with bigger data sets, it can become unwieldy to debug by printing and checking the output by hand. Here are some suggestions for debugging large data sets. Scale down the input. If possible, reduce the size of the data set. For example, if the program reads a text file, start with just the first 10 lines, or with the smallest example you can find. You can either edit the file themselves or better modify the program so it reads only the first n lines. If there is an error, you can reduce n to the smallest value where the error occurs. As you find correct errors, you can increase n gradually. Check summaries and types. Instead of printing and checking the entire data set, consider printing summaries of data. For example, the number of items in a dictionary or the total of a list of numbers. A common cause of runtime errors is a value that is not the right type. For debugging this kind of error, it is often enough to print the type of value. Write self-checks. Sometimes you can write code to check for errors automatically. For example, if you're computing the average of a list of numbers, you could check that the result is not greater than the largest element in the list or less than the smallest. This is called a sanity check because it detects results that are insane in the membrane. Another kind of check compares the results of two different computations to see if they are consistent. This is called a consistency check. Format the output. Formatting debugging output can make it easier to spot an error. We saw an example in chapter 6. Another tool you might find useful is the pprint module, which provides pprint function that displays built-in types in a more human-readable format. Pprint stands for pretty print. Again, time you spend building scaffolding can reduce the time you spend debugging. Yeah, it's all true. Dictionary, item, key, value, mapping, hash table, blah, blah, blah. These are all the glossary items. Definitely check it out. Moving into the exercise, ask an assistant. In this chapter, I said that keys in a dictionary have to be hashable, and I gave a short example. If you would like more details, ask a virtual assistant, why do keys in Python dictionaries have to be hashable? In a previous section, we stored a list of words as keys in a dictionary so that we could use an efficient version of the in operator. We could have done the same thing using a set, which is another built-in data type. Ask a virtual assistant, how do I make a Python set from a list of strings, and check whether a string is an element of the set. Exercise. Dictionaries have a method called get that takes a key and a default value. If the key appears in the dictionary, get returns the corresponding value. Otherwise, it returns the default value. For example, here's a dictionary that maps the letters in a string to the number of times they appear. If we look up a letter that appears in the word get returns the number of times it appears. Counter.get b0. If we Okay, well, why is get key default return the value for the key in the dictionary? Oh, okay. So counter.get actually gets this value and then defaults to this. I believe that's also similar to os.get because I think that's stashed as a dictionary as well, but that's a different story. If we look up a letter that doesn't appear, we get the default value 0, counter.get c comma 0. Use get to write a more concise version of value counts. You should be able to eliminate the if statement. More concise version of value, you should be able to eliminate the if statement. All right. Exercise. What is the longest word you can think of where each letter appears only once? Let's see if we can find one longer than unpredictably. Write a function named has duplicates that takes a sequence like a list or string as a parameter and returns true if there's any element that appears in the sequence more than once. To get you started, here's... Okay, so more fun stuff with dicts and lists and stuff. Write a function called find repeats that takes a dictionary that maps from each key to a counter, like the result from value counts. It should loop through the dictionary and return a list of keys that have counts greater than 1. You can use the following outline to get started. Okay. Good exercises, good exercises. Suppose you run value counts, okay. Words interlocking. I'm actually over reading all of these exercises. It's getting on my nerves. I'm going to try very strongly that the next video I make be continue the previous series of building apps with Fast API, because this is very boring and irritating for me, even though it's an exercise I really do need to get through, and honestly making these videos is kind of pushing me to do that. Yeah, I'm trying to think of a name for this series. Trying to think Python. I was thinking of something like pretending to be a beginner. Actually, I think I'll just call it that. Pretending to be a beginner. Yeah, I think that'll be the name of the series. Which is weird for you guys because you've probably been seeing the name for a while, but I am actually just now deciding that that's going to be the name because not even one of these videos is up yet. Anyways, thank you all so much for your time. Have a great one. Bye-bye.